So next, we are going to talk about differential gene expression with DESeq, or now DESeq2. Similar to microarray experiment, right? After you do this experiment, you do the quality control, you estimate the expression index. The next part is to look at differential expression. Are there changes when you knock out a gene, or you treat the cell with a drug, or between normal and some disease state, and things like that, right? So let's think about the distribution. Remember, for microarray analysis, before, well, actually, that lecture was from last year, from the recording. So for microarray, we have to check the data quality. If you are using Affymetrix array, now pretty much people believe that if you get an RNA expression index, which is already log-based, most of the genes across the different samples follow a normal distribution. Then there are a lot, like you can do t-tests or whatever, right, to look at the differential expression. But if the data is not following a normal distribution, you can use some non-parametric tests to see whether the samples in one group is significantly different from samples in another group. Similar to microarrays, for RNA-seq, we also need to know the sequencing read distribution. If you can model the distribution of the read counts, then we can use the correct statistics to calculate the difference. And so in terms of a read distribution, let's think about some very simple cases. Say, supposedly emergency room at certain hour on a day, you are asking, how many patients come in? Because it's a pretty sparse event. Think about it. The whole human genome is very big. The read that lands on somewhere is not that high, especially in the early days when people are sequencing like 5 or 10 million reads out of a genome that's 3 billion in size. And so the read landing in a specific location is very small. And so when the p-value, or at least the probability of having a hit in each location is very small, you are asking within the interval, right? Within 10 to 11 p.m., how many patients are going to really come? It's similar to ask, in the 3 billion base pair genome, within the 3 kb, what's the chance that you have X number of reads? Because each base having a read has a tiny, tiny probability. Within the 3 kb, it has some properties. Do you know what that distribution is? It's a Poisson distribution, yes. Poisson distribution has only one parameter, which is the lambda. It's the average event per interval. So Poisson distribution, if you write it out, is like this. This is the actual parameter. But if you say, what is the chance that in this 1 hour time, instead of seeing, so supposedly this hospital on average, within an hour, you see 2 events, 2 people come into the emergency room. So what is the probability on that day, within that hour, you will see 10 patients coming in the hospital? You can use this to calculate the probability. And so you can see, depending on what your parameter is, they have a different spread. So for example, so the Poisson distribution, the variance and the mean is the same. And so for example, if the parameter is 1, the average would be 1, which means like in this 1 hour, there will be just on average 1 patient coming in. But if it's 2 patients, 3 patients, 4 and 5, the probability decrease quite a bit, right? It's like this. But if on average within the hour, if it's like a big hospital, like Mass General Hospital, on average within an hour, you will get 10 patients coming in. That would also mean that the variation of this also increase. You can see the spread increase as well as the mean increases, right? So that's Poisson distribution. Initially, with high throughput sequencing, people were wondering whether this is going to be a Poisson distribution. However, there are some biases in the data. The sequencing data is kind of more noisy than Poisson distribution. In fact, if you, well, some of that could be because of GC bias. Some of that could be just whatever library preparation. It's just every step creates some systematic biases and also other things that we are not aware of. So if you look at the actual, this is the log of the mean expression. This is log of the variance. For a Poisson distribution, you should see things on the straight line here. Which means that the mean and the variance are the same for each gene. So let's just say even for the identical sample, if you do this experiment, like the same RNA, you put down the RNA-seq multiple times and you ask, what is the mean? What's the standard deviation? Let's just say you do it 10 times. You calculate the mean, you calculate the variance of the samples, you will get something like this. Which means that as your expression goes higher, the variation is high, and it's even higher than the mean. It's over dispersed compared to a Poisson distribution. And so after a while, people tried to fit different distributions, and now it's pretty much acknowledged that with RNA-seq or sequencing in general, the sequencing reads landing in a 3 kb region or whatever, some intervals, follow a negative binomial distribution. So instead of having one parameter in the Poisson distribution, negative binomial distribution have 2 parameters. Interestingly, originally negative binomial distribution is defined by the number of successes before the first R failure, if the probability of success is P. If you think about like a binomial distribution is like if the chance of flipping a coin is head or tail, you know, what's your chance? You do 10 coin, you get, you know, 8 head, or, you know, you do 200 coin, you get 120 head, or things like that, right? But it's like Bernoulli trials. But for negative binomial, you can think of this as also a coin flip, is the number of heads that we flip. If we get before we get the first tail, if the probability of a head is this small, is this probability. And so the property of the negative binomial is this is the mean and this is the variance. And so if we look at this again, compared to the previous figure in here, you can see here when the lambda is 1, this is the kind of the mean, and this is like this. But you can see here when the negative binomial, you know, RP is like this, you can see the spread is already higher, right? But when it's 10, you can see this spread is much, much bigger in this case compared to like this, right? Oh, so actually this is not the mean. Yeah, if the mean is 10, actually the spread also would be higher. So this is the coin flip way of defining negative binomial distribution, but you can also think about negative binomial in this way, which is you can ask, okay, what is the chance that in this sample on this gene, I'm gonna see this number of reads if, you know, we know that they follow some negative binomial distribution. There is a normalizing factor. We'll talk about that normalizing factor a little bit later. And this is the quantity of interest. This is the actual gene expression that you want to estimate. And this is the dispersion, or the kind of the variance, or the dispersion you want to give a gene. And so how is this dispersion calculated? So you can see here, in negative binomial, you can think of this is every gene has a mean expression level. They also have a variance of the expression among different samples. If this is Poisson distribution, the variance and the mean will be identical. However, since the RNA-seq reads have more noise, you use this little dispersion parameter to say, as the expression level increase, we use this squared multiplied by a little factor to to estimate the actual variance. So you can see here, this is like mean. Actually, yeah, if you can look at the, actually maybe like this, you can use this distribution. You can estimate at specific mean and at specific, what is the actual variance. You can estimate this scaling factor for the little, dispersion factor for the gene. And so this also, again, you can imagine if we were to calculate the variance of a gene based on RNA-seq, especially now people just do 2 replicates. You have 2 replicates of the treatment and 2 replicates of the control. You don't really get a very good estimate of the variance. However, if you look at all of the genes together, you can roughly estimate what that distribution should look like, right? So you can use this to help you shrink the variance. This is similar to what people do also in microarray as well. You estimate the variance of a particular gene, but you also use all of the other variants in the sample to help you estimate the overall trend. But you can see here, depending on where my mean is, that scaling factor might be different because the variance could be even bigger at a higher expression level. Okay, yeah. So given the parameters, so basically, if you have these parameters, you will know. You have the P and you have the R. You will know, what's the mean, what's the variance. Yeah. So now, if I say if a particular gene is supposed to be using this negative binomial parameters, but then after you do a drug treatment or a gene knockout, you observe this many. It's like this hospital normally comes in with these patient intervals, right? And suddenly I'm seeing a lot more or a lot less based on the original parameters. You can calculate the p-value just based on negative binomials. There's a equation, you can use it. So we want to mention also very quickly how to do the normalization. This is something also kind of interesting that DESeq considers. So initially, remember, we want to use the raw read count in the differential expression calculation, but we want to normalize it just a little bit. We don't want to normalize it all the way to like RPKM or TPM level. However, there's another small scaling factor. And I use this example also from Joshua Starmer, where it's looking at, in one sample, it has the expression of, let's just say very beginning, it's only 6 genes. In another sample, it's also the expression of this 6 gene. You can see this one gene is super highly expressed in one of the samples, but so even though the total reads of the 2 libraries are the same, you only give this sample 600 reads and they have to spread over all the genes. And if one gene has crazy expression level, it's gonna suck up all the reads and the other genes didn't really have a chance to get their reads. And so in RNA-seq, we do have to deal with this situation. If one gene is expressed too high, the other reads are all a little bit lower. It doesn't mean that the other genes are necessarily lowly expressed in one sample compared to the other sample. And so DESeq has another way of normalization. Basically, if a gene is expressed, say if it's super highly expressed in one but lowly expressed in other, those genes are eliminated. Basically, it uses most of the genes that are assumed to have reasonable expression and not too much fluctuation to estimate how much reads do they have, those genes have among the samples. So it's like, actually in the early microarray days, you can imagine if I take all the genes that didn't really have too much differential expression, they are fairly stable, and I calculate how much are those reads in first sample and how much are they, those reads are in the second sample. You realize that, for example, in the first sample, this crazy transcript is sucking up your reads, and the remaining really not changed samples didn't even have a chance. So you want to scale everybody a little bit, okay? And so they do a little bit of scaling factors in here. But also it try to stabilize or shrink the variance by borrowing information from other genes, which means if you only have 2 treatment, 2 control, you might be estimating a variance that's really not very accurate. And so you can imagine if we look at all the samples together or all the genes together, you can say, okay, roughly at this gene expression level, the variance should be around that. And so we use all the genes to estimate the trend or at least the distribution. And based on your observation, it adjusts a little bit, right? So if the original variation is too big, it will try to shrink. But if your raw data variation is too small, it will try to increase a little bit, just so that the variation is not 0. Because if the variation is 0, you will call a lot of genes as differentially expressed. Okay, so this part, you can see when people are developing differential expression for RNA-seq, they kind of learn a lot from the early microarray days on how to calculate differential expression. Okay, yeah, so we try to shrink or stabilize the variance by looking at all the samples together and all the genes to see roughly what is the variation of genes at that expression level. Okay, then you get the differential expression, but then basically K is the actual reads, mu is the mean expression, and the sigma is the variance. So you can calculate, whether the gene is differentially expressed based on the negative binomial distribution. And so this, you can use the DESeq2 to calculate. And so you can see, if we look at, this is the log fold change of the differential expression, and this is the mean expression. This is similar to a MA plot. Okay, remember MA plot is I think mean expression, this is already the geometric mean, right? This is the average, and the Y is the kind of the difference, the fold change in some sense. If you just use the raw data, you can see at the low level expression, you get very, very noisy result. And then you would call these genes as real differentially expressed, but then a lot of these other genes, you also call them, they would be kind of false positives. However, if you use DESeq to borrow information from all the other genes to estimate the variance for the variance stabilization, then you can see here, we can pretty robustly call these genes as differentially expressed, and then eliminate those genes as not quite differential. Okay. Yeah, so the shrinkage is not equal. You have, yeah, so strong moderation for low information genes. So these genes really don't have much information, right? They have low counts. In fact, later on, DESeq can even completely eliminate them. Yeah, so this, once the expression level is high, the variation you can estimate more accurately. In fact, DESeq has even better ways to adjust for these kind of low information counts. But before that, I want to ask you guys, do we need to worry about multiple hypothesis testing for DESeq? Yes, because we have 20,000 genes, right? Every gene we have to compare the 2 conditions, ask whether they are different. And by chance, there could be genes that are different, so we need to have an FDR adjustment. And so for DESeq, in addition to using Benjamini-Hochberg for adjusting for multiple hypothesis testing, DESeq also try to remove the lowly expressed genes, because if this gene is so low, even if they're, say if their read count is low, either because the gene is too short or the expression level is too low, you just don't have enough power to detect that. And so if you can reduce your total number of tests, then your FDR, you can actually identify more correct genes because you remove those hopeless ones from contaminating your results. And so for example, for DESeq, it can do something like, if the average read count of this gene in all the sample is below a certain cutoff, then forget about that gene. It's hopeless. We are not even bothered. And another algorithm, which is called EdgeR, it's the group that developed Lima. They also say if in, say, we're doing a group-to-group comparison. If, say, like this particular gene doesn't have over 1 read count per million in over 2 samples, then forget it. Because even if it's very high, but on only 1 sample, you will never have enough power to call these 2 conditions as differential expression. Then you can also eliminate that. But a lot of times you can use, at least for DESeq, this particular cutoff, where to do the cutoff can be determined by the real data. For example, for DESeq, it tries to see where do we cut off, what's the average read count that I need to cut. And then they ask at the same 5% FDR, what is, so at the 5% FDR cutoff, am I able to call more genes as differentially expressed? And you can see here, initially, if you don't do any cutoff, maybe you don't do so well, but then as you increase your cutoff to say, okay, those ones I start to eliminate, you can see at the same FDR cutoff is able to call more genes as differentially expressed. But then as you continually increase, then eventually even the corrected good genes get eliminated, then you decrease again. And so DESeq automatically tests this. And then in this case, it will pick a correct cutoff. I think in this case, it will eliminate half of those genes that are really low. Well, depending on the data, of course. You can eliminate, say, 20 or 30% of the original data because they have very low expression. So just don't even consider them in your multiple hypothesis testing. That will improve your power, okay? And so at the end, you use Benjamini-Hochberg, at least for DESeq, for FDR correction, okay? I think just for remaining a little time, we will not have time to really go over this algorithm, but at least we want to show you that you can potentially use it. Because from the same gene, you might have multiple transcripts because of splicing. There are algorithms to do these type of splicing. The first is just isoform abundance estimation. If we already know the transcript, remember for homework 2, for the same gene, you could have different transcripts, and some of them are already very well annotated. In fact, for both Callisto and salmon, it's already annotated. You just use each transcript and map the reads onto there. That can be done, and you can calculate the differential expression of the transcript in between the samples, right? But there are also de novo approach, which is we just want to see how many total, so when we say isoform, we are talking about a full length transcript. And so there, if you don't know for sure, cufflinks can help you assemble into some transcript and another. So from one RNA-seq sample, it can assemble multiple transcripts. And so there, algorithm called cufflinks can do this. It doesn't do it as well. I don't think it's as much used. For real people who care about splicing, they very often just care about a single exon. They say this exon, in one condition, it's really, so for example, in this case, supposedly in one condition, this gene is splicing like this. It's using exon 1, 2, 3, but in another condition, it jumps over. It's only using exon 1 and 3, and the second one got eliminated. And so very often for the people who care about splicing, they don't do the whole transcript, because sometimes the first exon splicing and the last exon is really far away. You don't really have a power to detect that, but you can detect whether a particular exon is being differentially spliced, and there are some algorithms for that as well. And then for de novo transcript assembly, this is, say, if there's a new monkey species that the whole genome hasn't been done, or a new hybrid rice, you don't know the genome or whatever, then yeah, if you don't even have the genome, you can use Trinity to assemble those transcripts, and it can also calculate the assembly and then do differential expression. But in this homework, for now, we're gonna do very simple non-transcript, so we do the salmon mapping, and then we use DESeq for differential expression. Okay, yeah, so in summary, so RNA-seq, make sure you still do careful experimental design, try to avoid batch effect. For read mapping, we want to use the splice aware aligners like BWA, not BWA, we want to use STAR. For quality control, you can use RNA-seq. For expression index, we use like FPKM, but probably TPM is a better estimate. But recently, there are also pseudo aligners like Callisto and Salmon for just known transcript. For differential expression, DESeq is definitely still the most popular tool, especially if you don't have enough samples. If you have like 100 cancer, 100 normal, a lot of tools will be okay. For DESeq, it uses negative binomial distribution to model the over-dispersion of the read coverage on a gene. It uses hierarchical model to stabilize the variance, borrow information from many genes. And also it tries to remove the very low content, lowly expressed genes to reduce the total number of hypotheses to test in order to give you more differential genes. And then there are some other tools that do the more fancier functions. Okay, great for today.